Welcome to the Deep Dive. Today we're peeling back the curtain on a really specific challenge.
Yeah.
How do you get a machine to spot credit card fraud when, fraud itself is an incredibly rare event?
Exactly. And this isn't just theory. Our source material for this is, well, it's basically a complete blueprint. It's a code pipeline that shows you step by step how to build one of these fraud detection systems from the ground up.
So the mission here isn't just about building a model. It feels like the mission is really defined by the data itself. Before we even get to algorithms, what's the biggest hurdle this whole thing is built to solve?
It's the central problem, and you can't avoid it. It's extreme data imbalance. So get this. In the data set, there are 284,807 transactions.
Okay.
But only 492 of them are actual fraud. So when you do the math, the total fraud rate is just 0.1727%.
Wow. That's practically nothing. So the system is, by default, almost guaranteed to never see the one thing it's looking for. So we're looking for those knowledge nuggets. How do you engineer a model that can find that one tiny needle in a massive digital haystack?
Okay, let's unpack this. How did they even start preparing the raw data? All right, so that initial look at the data, it reveals a structure that's clean but a little weird. You've got two normal-looking features, time and amount, and then 28 others just called V1 through V28.
Right, and we're told those V features have already been through principal component analysis, or PCA.
Which is a huge time saver, right?
Oh, a massive shortcut. It means the data scientists don't have to get bogged down trying to figure out how all these raw variables are related to each other. They can just jump straight into modeling. And, the sources also confirm something that's basically a data scientist's dream.
What's that?
Zero missing values across the whole data set.
That never happens. Okay, but what about those two original features, time and amount? I mean, PCA might have scrubbed out some important context there. It might have, and that's exactly why the pipeline tackles them right away. The raw time feature is just seconds from the first transaction in the data set. That's totally useless for finding any kind of pattern.
Right.
So the very first bit of feature engineering is key. They convert that raw timestamp into the hour of the day. It's a simple calculation. You just divide by the number of seconds in an hour and see what's left.
And what does that show you?
Well, the visualization in the source material makes it crystal clear. Fraud isn't random. It clusters at specific times of day. That's a crucial behavioral signal that the raw time variable just completely hid.
These engineered features, they sound almost too simple, especially next to those 28 complex PCA variables. Why even bother making a basic flag like, is it nighttime, when the model already has so much complex information?
They bother because that simplicity is directly tied to human behavior, and that often has huge predictive power. So the model goes beyond just the raw numbers and creates these contextual nonlinear flags.
Okay, like what?
First, there's is night, just a simple yes/no flag for transactions between midnight and 5 a.m. Second, high amount, which flags anything over a certain threshold, like say $1,000. And then the third one, which I think is the most insightful.
It's a combination.
Exactly. High amount night. A flag that's only true if both of the other conditions are met.
A high value transaction in the middle of the night, that just sounds like a high risk signal.
It is. The analysis they included showed that these new features had an extremely high correlation with the fraud label. So by engineering a feature like high amount night, you're basically handing the model a massive predictive shortcut. You're setting it up for success before it even has to deal with the imbalance problem. So once the features are engineered, we get to the main event, the balancing act. The first step is pretty standard. You split the data, holding back 20% to use as a test set. But crucially, they use stratification.
Stratification. So that makes sure that the tiny percentage of fraud cases gets represented equally in both the training and the testing groups.
Right. Exactly. You don't want to accidentally end up with 0 fraud cases in your test set, but you're still left with a training set that is 99.8% legitimate transactions.
And if you train a classifier, like the random forest model they use here, on that really biased data, what's the big risk?
The model learns nothing useful. It'll just look at the massive majority and learn the simplest possible rule. Just guess not fraud every single time. It would be 99.8% accurate and completely useless. It would miss every single case of actual fraud.
Which is why you have to manipulate the training data. The sources say they decided to aim for a 10-to-1 ratio of non-fraud to fraud. How did they get there? What techniques did they explore?
They tested 3 different methods to see which one worked best for this specific data set. First up is random undersampling, or RUS.
So you just throw away most of the normal transactions.
Pretty much. You just randomly delete examples from the majority class until you hit that 10-to-1 ratio. It's really fast, but you risk throwing away a lot of important information about what normal actually looks like.
Yeah, you could lose valuable context about legitimate spending.
Precisely. Which brings us to method number 2, SMOTE. The synthetic minority oversampling technique.
Okay, that sounds more complex.
It is. Instead of deleting data, SMOTE creates it. It looks at the existing fraud data points, and then it generates new synthetic fraud cases that are statistically similar to the real ones until you hit your target ratio.
So it's creating ghosts in the machine. Doesn't that risk, I don't know, causing the model to learn from noise? Or just blurring the lines between what's fraud and what isn't?
That is the number one risk, yeah. If the real fraud cases are already kind of ambiguous, PRAUC can just make that worse. And that leads to the third approach, which tries to get the best of both worlds. It's the combined approach.
Undersampling plus SMOTE.
Exactly. So first they apply generate more fraud examples, and then they apply undersampling to reduce the number of normal transactions, but they use a much gentler ratio. The idea is to get the benefit of those synthetic points while also reducing the overwhelming noise from the majority class.
And here's where the blueprint gives us a really crucial insight, right? They aren't just picking one method and hoping for the best.
No, not at all. They treat the data prep itself as an experiment. They train the exact same random forest classifier on 4 different versions of the data: the original imbalance set, the undersampled set, the SMT set, and the combined set.
So now we have 4 different trained models.
Right. And now we have to figure out which one is actually the best.
Which brings us to defining success. We already know that with data that's 99.8% non-fraud, just looking at accuracy is totally misleading. If you choose the wrong metric here, you end up with a model that looks great on paper but fails completely in the real world.
Oh, absolutely. The pipeline uses a detailed classification report, but for actually picking the winning data strategy, they focus on 2 specific scores: ROC-AUC and, more importantly, PRAUC.
ROC-AUC is pretty standard for these kinds of problems.
Yeah.
But the sources are very clear. PRAUC is the one that really matters here. Why is that? Why is it better than its more famous cousin in this exact scenario?
Well, ROC-AUC plots true positives against false positives. And while it's better than accuracy, it still gets influenced by that massive number of true negatives, the correctly identified normal transactions. PRAUC is different. It stands for Precision Recall Area Under the Curve.
Precision and recall.
It focuses specifically and exclusively on the performance of the minority class, the fraud cases we actually care about.
So it basically ignores the 99.8% of normal transactions and just zooms in on how well we're doing on that tiny critical group.
Precisely. It plots precision, which is, of all the transactions we flagged as fraud, how many actually were, against recall, of all the actual fraud cases that happened, how many did we catch?
And there's a huge business trade-off there. Low recall means you're missing fraud and losing money. Low precision means?
Low precision means your fraud team is spending all day calling angry, innocent customers. You're creating a huge operational cost and a terrible customer experience.
Right, that makes perfect sense.
So by picking the resampling method that gives the highest PRAUC score, the pipeline guarantees it's selecting the model that is fundamentally best at telling the difference for that rare positive class.
Okay, so we've used PRAUC to pick the best data preparation method and the model that was trained on it. Now that winning model goes into a kind of hyperparameter boot camp. How does the pipeline refine its champion?
The model gets put through a process called grid search CV. This is the final tuning phase, and it's critical that they use 5-fold stratified K-fold for the cross-validation.
So even during this intense testing, they're making sure that tiny fraud ratio is preserved in every single fold.
Exactly. You have to keep the imbalance problem solved at every stage. And the metric they're optimizing for during the search is average precision, which is directly related to that PRAUC curve we just talked about.
And they're tuning things like the number of trees in the random forest.
Right. But even when that's done and they have the perfectly tuned parameters, the pipeline knows one last thing. The standard 0.5 probability cutoff for flagging a transaction as fraud is, well, it's completely arbitrary.
This is the real-world step. The model gives you a probability score, but a human or a business rule has to decide where you draw the line between suspicious and fraud.
That's it, exactly. And this is where the business trade-off gets hard-coded into the final system. The final function, find-optimal threshold, understands that a false negative missing a real fraud case is way more costly than a false positive.
So it's not just looking for the mathematically best threshold.
No, it was given a very specific, non-negotiable constraint.
And what was that instruction?
The function was told to find a threshold that guarantees a minimum recall of 85%.
Wow, okay.
And then, within that constraint, it had to find the threshold that also maximized the F1 score, which is the balance between precision and recall.
That's a fascinating mandate. So they aren't just chasing some theoretical perfection. They're programming in operational security. They're saying, we must catch at least 85% of all fraud, period. And then, once that's guaranteed, they find the best possible balance.
It's the final synthesis of business policy and machine learning. And the output is just a single number. Maybe it's 0.28, maybe 0.41. That becomes the final operational cutoff. Any transaction with a probability score above that number gets flagged.
And that delivers the final product, the optimized model, trained on the best resample data and calibrated to a specific business-critical threshold.
So what does this entire process mean for you, the listener, taking this all in?
Looking back at this whole blueprint, it feels like there are 3 huge takeaways for anyone who's going to tackle one of these highly imbalanced data problems.
I think so. First, you have to accept that extreme imbalance and address it head on. And, treat your resampling strategy like a parameter you need to optimize, not just a choice you make once.
Right. And second, never underestimate just how powerful smart feature engineering can be. Simple contextual flags like isNight can give your model these immediate high-value signals to work with.
Mm-hmm. And third, you have to make that critical shift in how you measure success. You have to move away from accuracy, even from ROC-AUC in many cases, and really embrace PRAUC for model selection. And then that final step.
Optimizing the decision threshold to meet a specific business need, like guaranteeing you catch at least 85% of the fraud.
And that last point leads us to our final provocative thought. This pipeline did an amazing job optimizing a random forest model. But we have to remember that the core 28 features, the V1 through V28, were already highly processed with PCA.
So they were anonymized, transformed.
Yeah.
Exactly. So we have to ask, is the nonlinear tree-based structure of a random forest really the absolute best architecture for that kind of pre-cooked, transformed data? Or could a fundamentally different model, maybe a deep neural network, have found even more subtle patterns in those specific feature types? The choice of model is always influenced by the data you feed it. Which would you choose for your next deep dive?